So I got a wonderful looking slide deck because I stole the Google I/O slide setup thing, which sounded great in theory until I realized that I needed to rewrite the rendering thing that generates that kind of HTML and then fiddle with it a whole lot. So I guess tip for new players, just use Keynote. Really just use Keynote. I'm here to talk to you today about some, I guess, hard-won lessons about a high-throughput Erlang system that I work on at Heroku. It's a system called Logplex. My name is Geoff Cant, and I work on the routing team at Heroku. I've decided to dedicate this talk today to PagerDuty and the infinite sadness. Not only because it woke me up at 4 a.m., but because I guess PagerDuty is almost the reason that I write Erlang systems. PagerDuty is the thing that sends really annoying alarms to your phone, and then you've got that alert tone set up so that it sounds like a submarine dive alarm. It's a generally unpleasant thing, but if you have a production system that people care about, you will have a PagerDuty account or you will have some kind of equivalent. And I guess I write Erlang because I get less pages that way, mostly. So this is not actually a slide about my incipient retrograde amnesia. I work on the routing team at Heroku, and the routing team has two reasonably important jobs, two reasonably important systems that we work on. We have our big front-end HTTP load balancer. Now, Heroku is a company who is a platform as a service company for hosting complicated web applications in the cloud. And all of these applications work over HTTP. So the front-end load balancer that distributes incoming requests to the correct applications and sends the responses back is a reasonably important system at Heroku. And we also work on another system, the syslog router called Logplex, which is mainly what I'm talking about today. And I've included a couple of links to my GitHub account, which has some sort of relevant bits of code and assorted snippets and stuff and things, and a link to Heroku's GitHub account, where you can, in fact, find the source code for Logplex. So what is a Logplex? It's a syslog collector and emitter. So on the Heroku platform, we have lots and lots and lots of machines running, some order of magnitude larger than that number of pieces of applications. So copies of people's web server, our own infrastructure software, all kinds of things, doing all kinds of jobs on that platform. And they all need to write logs somewhere. But we're running on EC2. Disk is not really that fast and is prone to go away when you really don't want it to. And also, if you write logs to disk, well, great. You've done sort of about 1% of the problem, because getting those logs to a place where you can read them is kind of maddening. So the approach we took is kind of the standard thing that you do when you have a large collection of Unix machines, is we run a remote syslog. So the Logplex is the remote syslog destination for everything. All of the messages coming from customer code, from our own code, from the platform itself, they all get routed through local syslog daemons to this big cluster called the Logplex. Each of those messages includes a little token in it, which lets us work out how to route those messages to people interested in them. So that you can think that the messages are usually about some kind of topic, and that's usually going to be an application or a piece of infrastructure or something. And frequently these topics are divided by customer, so you don't really want messages for one customer's topic ending up in another customer's topic. Because getting all of the syslog messages in the universe to one place is a useful but not sufficient task, we have these things which in Logplex land are called drains. It's where you configure the system to deliver all of the messages about a topic to some destination. And at the moment we have UDP, TCP syslog, and a slightly crazy syslog over HTTP variant that we use for delivering those to third-party logging providers, other people's remote syslog servers, that kind of thing. Logplex allows you to sort of modify the configuration of the system at runtime, create new topics, change where their output is posted to, all that kind of thing. It has a little HTTP API to do that. There's one kind of nifty feature, which I haven't seen in a lot of other things. It has a mode where it will do effectively tail-F on a topic for you. So you can use the command line client and say, I would like to, get logs with a tail for this thing. And the system uses Erlang distribution to collect all of the messages from those various nodes in the cluster to one place so that they can be delivered to your web browser. And if you're interested in the mechanics of that kind of stuff, there's a link here. When the slides are online, you'll be able to go and see the Logplex open source and see how that works. So this is the infrastructure, or I guess logical system diagram that I usually pin on a nameless 5-year-old, but is in fact me trying to draw on an iPad. Messages have tokens. The token determines which channel a message is sort of notionally passed through, and then channel output is multiplexed to drains, output destinations, possibly tails, and we maintain a bit of a ring buffer in Redis so that you can get the sort of, when you do the tail command, you want to be able to get a little bit of preceding history, but we can't afford to keep everything. So that's where that stuff is. So, high throughput Erlang systems, my usual approach. If you can apply back pressure, do. I'm not quite sure if I am quoting someone here, but I should be. Active once is fantastic. It kind of automatically gives you rate limiting and back pressure. Your client's slowed down to an input rate that you can handle. Wow, job done, great. Short presentation, hope you've all enjoyed it. Oh wait, there are more bullets on the slide, damn. Logging systems generally can't do this. And I'm going to get to why in a second. So this is, yes, the final part of my usual approach. So a brief note on syslog, the protocol. It's the worst. Sender says to the receiver, connect, data, 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 and the receiver says, nothing at all. There's no application layer acknowledgements. So the receiver can really only slow down the sender by stopping receiving, and you either just stop reading off the socket and then the sender's TCP buffers eventually fill up and it stops sending, or you close the connection, in which case they will probably just reconnect you and start sending again. And because there are no application layer acknowledgements, like when that connection gets cut, and particularly if it gets cut due to an error, like packet loss or your load balancer went all psycho on your connections, which seems to happen more often than you might expect, the sending side doesn't know how many messages it actually successfully delivered. So syslog. Even the message framing format, like working out where one message stops and another one begins, kind of unreliable. There are at least two schools of thought that I've seen in the wild. One is we use new line termination, which is fantastic, except that now you can't put a new line in the middle of a message because there's no escaping rules. And then the other one is length prefixed, and you're like, well, that's a reasonably sensible choice. And you're like, well, yes, except for the fact that the ASCII encoding of the integer that specifies the length of the message looks an awful lot like a Unix timestamp. And it'd be really bad if we confused our message boundary and started trying to read a 1.5 gigabyte message. And you're like, well, okay, sure, but I mean, people connect to you and they're at least going to send you the same kind of framing format on one connection, right? Yeah, not so much. So Logplex has this kind of weird recovering syslog parser where if it gets confused, it starts dropping bytes until it finds something that might be a message boundary and then tries to see if it's length framed. And if that works, we'll do that. Otherwise, we look for new lines. Misery and pain. Well, at least syslog, the protocol, is pipelined in that there is nothing that the receiver can do to slow the sender down. And it has, reasonably minimal encoding and decoding complexity. I'm looking at you with daggers in my eyes, JSON. So then, the pickle that I am in. Nobody wants to slow down what they're doing to guarantee log delivery. Or at least, those people exist, but they're a bit of a vanishing minority. When we're talking about the usual case for logs, people really kind of want it to operate sort of like it's always done. They do a whole bunch of stuff, write atrocious amounts of garbage to syslog, and then expect syslog to deal with it. And then they'll get annoyed if you lose messages, but not as annoyed as if the thing reading off of their standard out, collecting their log messages, maybe stops reading off of standard out. That generally makes them very angry. So that's the sort of sender side of that. And then when we are being a remote syslog receiver, the pickle we have is that if we don't accept messages, then the sender is going to drop them because their buffers are only so big. And if we close the connection, then the sender will drop the messages and a few extras just for funsies. An extra wrinkle in this little pickle is that a sender's connection full of syslog messages, those messages might be for different clients or different topics. So it's actually unfair to slow down one of these connections by just reading slower or dropping messages off of it, because that's unfairly penalizing random people who happen to be on that same connection. It's a pretty miserable little problem. So I inherited the system about a year ago, and the input side was just not really keeping up with senders. So the first things I did, I started with the basics. Looked all through the input side to work out, was it accidentally serializing? Was it making gen server calls to a gen server where the M to N of input processes to gen servers is not 1-to-1 or better? Any gen server call in your input side is probably suspicious if you need to run at a ridiculously unbounded input rate. Its table reads, they seem to be fast enough in practice. Read concurrency, I guess, is an option in later VMs, and that seems to improve matters. But I guess if the table that you're reading from is not being written to all that much, it generally works even without that. Okay, cool. Done all that. Input side, kind of under control. Look through it, no gen server calls. Wait, what? This is the message of doom and pain that you get. So now we're so good at keeping up with the input volume that we're blowing out the message queue on the output side of the system. And we run out of heap space, and the VM goes to allocate and goes, give up completely. Can't add back pressure to the input side because we're a logging system when we already decided that we can't. The output side is tricky. Sometimes you're not connected to the destination, either because this is the first time that you've tried, or the connection was interrupted for some reason. There was packet loss, or the other end crashed and restarted. Sometimes we're not connected. And you kind of go, okay, well, I guess I could drop messages while I'm not connected to the other end. It's not ideal, but really, what more do you want from me? I can't store these messages on disk because there's only so much disk in the world. And frequently it's very, very, very slow disk in the cloud. Okay, well, all right, we'll compromise. We'll drop messages if we're not connected to the other end. Then your other end will turn around and do this to you. They will run too slowly. And you will still blow out your message queue because you're busily, slowly pushing messages into the TCP connection, and they're reading them really slowly. And your message queue is just going do 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 do. All right. Pretty sure I promised in the talk description that there would be some tricks. As the graphic on the slide may indicate, these tricks, they come at a cost, and so I don't recommend them unless you have to. Here is a kind of dumb, retarded trick, but it may staunch the bleeding. This is a dumb check that you insert in the middle of one of your output side processes, and you check your own message queue length, and if it's greater than some number of messages, which probably represents a large amount of memory, commit suicide. Give up. You'll probably be restarted if your supervision tree is set up correctly, and you've just dumped a reasonable amount of messages without having to read them and process them if you are like tremendously slow. This is one of the things where having separate memory spaces and message copying in Erlang is great. If the process dies, all its memory gets collected straight away with no muss or fuss or anything. So, I mean, this is terrible. I'm telling you to have your processes commit suicide because they're going too slowly, but you know, sometimes this will get you through the week that you need to patch your system so that it runs well enough that you don't need to do this anymore. I guess I would also recommend taking it out after that week, because otherwise it will just sit in there and then everything will run along fine for months and months and months, and then there'll be some other weird thing goes wrong that causes a thing, which causes the thing, and then the process goes poof, and you go, why did that happen? Oh. All right, so dumping the message queue unceremoniously is obviously not ideal. So in that week that you bought yourself, you think, right, bounded buffers. We'll move that memory from the message queue into the process heap. And why would we do that? Well, that lets us limit the size that can be. We can't limit, like Erlang gives us no primitives for limiting the size of the message queue or the size of the process heap, because the process heap is part of, the message queue is part of our process heap. But we get no control over limiting that growth. So the only way you can limit it is to pull all of those messages into the process heap and limit it there. And because this is a logging system, we can generally decide to discard the oldest input to meet our memory space requirements. Because when you do have to drop messages, the most recent messages are generally more important to people than messages that occurred half an hour ago or whenever. Cool, okay, we bounded our buffer size, we drained messages into our process. Aren't we now silently losing messages? It's like, yes we are. It's no longer as noisy as the entire VM exploding and Nagios going off and PagerDuty waking you up in the middle of the night. But silent message loss is not a great characteristic in the logging system. So what we can do is we can keep track of the loss, at least. When we displace a message in our little bounded buffer running in our process, we can take a timestamp of when we start doing that, and we can keep track of the number of messages that we have to displace. Then when we grab stuff out of the buffer, we insert a fake message into the retrieval where we say, like, you lost this many messages since this time. And that's actually a pretty helpful thing. It means that people no longer look at their log stream that they've maybe saved to Papertrail or Loggly or somewhere and go, well, my process was running fine here, and then something, and then it continued, and it jumped over a whole bunch of lines of code. A logging system lying to you is almost worse than no logging system at all. So explicit loss has been a really useful trick in the context of Logplex. So the version 0 of the code, a whole lot of messages, they go into the message queue, the output process reads off the message queue and sends to the TCP port, reads off the message queue and sends to the TCP port, and that explodes in your face. So then we move it in process, and a whole lot of messages, we read them really quickly off the message queue and we put them in the bounded buffer and then we send to the TCP port. And we read some more out of the bounded buffer and we send to the TCP port, and we read from our message queue and we put things into the bounded buffer and so on and so forth. And that's great. But sometimes a gen TCP send will take a really, really long time. And because of the law of infinite perverseness of software or something or other, that will happen at a time when you're getting a whole lot of messages being put in your message queue. Now, while you are blocked trying to do that gen TCP send, like nobody else is slowing down, they don't care. So you run out of memory and your VM explodes yet again, just when you thought you were over this. So we'll add a timeout. We'll call gen TCP send /3. Ha 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 ha. No, that doesn't exist. Which I guess got me curious. Because here's like a weirdly synchronous call in the middle of Erlang, which is generally all about the asynchrony. So I got curious, like how does gen TCP work under the hood? And is there any way that we could turn that synchronous call into an asynchronous call, or maybe a synchronous call with a timeout, something like that? It was only a very large amount of time later that I learned about the send timeout option that exists on gen TCP ports. It's a bit of like the option that you set on a port affects all sends, and it's always the same size of timeout. So it's, yes, I appreciate that Erlang makes some attempt to give you this functionality, but I'm not convinced that it's really the answer. So to the rabbit hole, let's find out how gen TCP actually works. So when you call gen TCP send, it does this kind of weird thing where it goes to the inetDB, whatever that is, and it looks up the socket, and it gets back this module, and then it uses the send operation in this other module to actually do the sending. Okay, well, that's curious. And so you trace through the code, and it's kind of all squiggly and back to front and upside down, because this is some of the oldest code in the Erlang distribution. Like, this has been around since it had TCP. And it gets a bit confusing. So skip over a lot of investigation. Mod always turns out to be prim inet for TCP ports. And it has this weird little trick where there's an undocumented call called Erlang port get data. Apparently you can attach a term to a port and then retrieve it later. And I guess at some lightning talk in the future, I'm going to find a horrific way to abuse that and make Kenneth and the OTP team exceedingly mad at me. But anyway, so if you go into prim inet and look at its send operation, it deals with some option lists, and it deals with a bunch of error handling and some other stuff. But I guess the important part boils down to this. The port command to send data down the socket kind of returns immediately, and then it waits around for a reply message. And you're like, okay, so under the hood, this is all async, and you just won't expose this to me? All right. This is a production system. I'm one day from retirement. I play by my own rules. We could just do what it does and add a timeout. Okay, sweet. What I actually did in practice was did the fully asynchronous version where I do the send and I start a timer. And so the send completion event will either be a timeout message or it will be one of these inet reply messages. So I can continue to process my message queue and not be blocked while I wait for the send timeout. And you can take the code that's on the slide and kind of work out how to do the message version. Logplex TCP syslog drain is a module in the open source distribution that you can look at to see how precisely we did it. I guess we turned a two-state finite state machine of we're either disconnected or we are connected and ready to send into a three-state thing where we are disconnected or we are connected and ready to send or we are in the process of sending. But the neat thing is that in none of those states are we blocked on anything. Like we can always process our message queue and maintain that bounded buffer. Great. This was kind of the first approach that I took to creating one of these high throughput processes, and it does work. It's in production right now. The approach was basically make all the synchronous operations asynchronous, no matter how much tracing through the bowels of OTP you have to do to get there. We don't spend much time blocked. We can drain our message queue, but the code complexity has gone way up, like quite a ways up. So there's a cost to be paid for this. And we have to be really, really careful when we add third-party libraries into the middle of our code now. Because if they accidentally do anything that might block, you're back to square one and your message queue blows out and the VM explodes. So you end up with a process that is high throughput and it does work and it does deal with a whole lot of receiver faults and failures and slowdowns and that kind of thing, but it's fragile. So that was the TCP syslog stuff. Then it came time to see if we could add like an HTTP transport for syslog, which I know sounds crazy, but there are worse ideas out there, believe me. You can go Googling for some. Some of those things, man oh man, you can talk to me about it afterwards. So for the second time around, I decided, why not do the Erlang-y thing? Add more processes. That generally seems to be the solution to many things, except possibly having too many processes. So I guess what the approach was here that I was trying to change my output side. I needed to add an HTTP client to generate the request body, like format the command that we're going to shove down the TCP socket. But I guess more importantly, I had to add code for watching the state of that connection, because it's no longer I'm connected and I can send. It's like I'm connected and I sent a thing and I have to wait for their response and then read through the various bits of their response before I'm allowed to, like send again, unless they allow pipelining, which is something I hadn't thought of. But the TCP syslog stuff that I had, it was really complicated to add more states to that thing. And if you get any of them wrong, you stop reading from your message queue and it explodes. The other thing involved is Erlang's new SSL implementation. And this was kind of around the early R15 series where Erlang's new SSL implementation was seriously rough. And it had a number of operations which just every now and again were just not complete at all. You would do the call to like connect, or to send some bytes on the wire, or to receive off of the wire, and it would just stop. It would just sit there forever. Even better yet, the TCP connection was still established. I don't even know. But when you add that kind of like unreliability in a library that you need to call in this process, which is maintaining its bounded buffer, the complexity was impossible for me to deal with. So I moved the bounded buffer to a separate process. I changed where the messages got delivered into it so that they would be delivered not to the drain process itself, but to a buffer process. And then in order that I didn't have to have infinite amounts of back and forth between the output process and the buffer process, like I certainly didn't want a whole like, I have a message, okay, give me the message, here's the message, give me a message, here's the message, da, 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 da. Because doing that once for every message, I mean, that's like the amount of work you have to do grows proportionally to your input, and that seldom works out well for me. So instead, the bounded buffer I arranged so that it would have a couple of states. It's either empty and receiving messages. Once it has any messages at all, it notifies the output process that it has some data for it. And then the output process asks for a bunch of messages, and it gets back a message containing a bunch of messages. And then I got really fancy, possibly a little overly complicated, as Fred will discover in a couple of weeks. in that I could send a function over to this buffer thing where I could have it actually frame out the messages so that I could ask for a number of bytes worth of messages out of this buffer. And so it would read a message out of the buffer and encode it and add the framing and give me back basically an IO list and just keep track of the size and then keep doing that until it had got, say, like 4 kilobytes or like up to 4 kilobytes of data, and then return me this like 4 kilobyte chunk that I could put on the wire. And that was an interesting idea, to be honest. I haven't done enough performance measurement to know if the idea was worth it, but it is a definite improvement over the give me a message, here's a message, give me a message, here's a message. So this slide in the web version will link to the modules in Logplex which implement this idea. Yeah, so I guess the first version, even doing all of that, still didn't work. And that's because my SSL operations were unreliable. I would try and connect, or I would try and send, or I would try and do some other thing, and it would just like totally sit there and ignore me for the rest of time. And the worst thing about it is that it didn't crash. Like, at least if it crashed, then supervisor restart would kick in and we would at least make some progress, because this event was relatively rare. But it didn't. It just sat there, and the TCP connection was fine, and the other end's going, dude, where's my data? Yeah, no good. So, the put children to work scheme, add more processes. You've got some kind of unreliable library that you looked at and we went, I know I have to include one of these to make it go at all, but I have a bad feeling about this. Spawn a child. Get them to do the library operations. Don't let them fail you a first time. So what you can do is move that potentially unreliable operation, and I mean, really, I'm teaching a large collection of grandmothers to suck eggs here, but you can move that operation to a sacrificial process. The connect work happens when you spawn it. Maybe it will send you a message back to say, hey, I'm ready for data now, because maybe you want to track how long it's taking to connect to things as an indicator of their health. You can pre-spawn them if you want to be already connected to this destination before data even comes in. And then they just sit around and they wait for a message of like, here is the data I want you to transfer, now go do it. And give me a call back when it's done. You also have to start a timer at that point, because just like with async TCP send, the completion event is either going to be your child saying, look at me, I've achieved. Or it's going to be a timeout saying they got lost in the woods. And yeah, just give up on them. You can either immediately start connecting, you can just kill them off at that point. It's like they failed for some reason. Did they fail because DNS lookup took too long? Who cares? Did they fail because the TCP connection was going too slow? Who cares? Like, if your destination, like most things in the cloud, I guess these days, the destination will be, will have a whole lot of machines behind it serving it. So a failure of almost any kind, retrying will usually get you the result that you want. Especially in the case of like a TCP stall, because a packet got dropped and now some timer thing is going on. Who cares? Just retry it. So you can kill and retry it straight away, or an idea that I had that I haven't tried is you retry straight away and you just leave that client sitting around for a while, and maybe delay killing it off, because who knows, it may come back to its senses. Erlang start timer /3 is a fantastic function, and you should get familiar with it if you have not already. Okay, to sum up. If clients in a logging system refuse to slow down, then they've basically chosen message loss as the way to smooth over the fact that they will produce too many logs at some point for the system to cope with. The amount of variation in the volume of logs that somebody can generate is quite frankly astonishing, because it's one thing if your web server goes along and it gets a request and it produces one line of output Apache style, saying I responded 200 and here was a user agent and some other stuff and things. Sure, that's the usual case. They generate 10, 15, 50 messages a second. Dealing with that's pretty fine. Then something goes wrong in their web process, and all of a sudden a request coming in is like 5,000 lines of XML encoded stack trace. And the way syslog generally works, each of those are separate messages, so the message rate has gone from like 50 a second to maybe 50,000 a second. But they refuse to slow down. They don't want to like generate stack traces slower. That would be madness. So basically, they've chosen message loss. But they will be much happier with you if the message loss is deliberate and not deliberate in the, well, the Erlang VM couldn't allocate some memory, so it totally exploded and threw shrapnel everywhere kind of sense. They will also be less annoyed if you make the loss explicit. Erlang being Erlang, going full async on almost anything is possible, but frequently comes with a rather large cost in terms of complexity. Sometimes it's worth it, sometimes not. And the answer is usually add more processes. All right, that's really all I have. And yeah, questions?
Do you have a problem, since you have a lot of processes and sockets and so on, do you have a problem with the run queue and the VM blowout? And do you change the priority of any key processes to try and balance it out?
Okay, the question was, we have a lot of ports and processes running in the VM. Does our message queue blow out? And do we change the priority of processes in order to deal with that? I guess the Amazon instance size that we typically run has 4 to 8 cores, and they seem to be beefy enough that the run queue size for us, I guess, hovers in the teens, and it seems to be generally okay. We haven't changed the priority of any of our processes. I think we might have included some libraries which have some slightly higher priority processes, but for the Logplex code itself, I don't believe it uses process priority anywhere, no. Somebody in the back.
At your 99th percentile, how big is your biggest log entry?
So the question is, at our 99th percentile, how big is our largest log entry? We have because of the problem I mentioned with syslog protocol parsing and a length header looking exactly like a Unix timestamp, we deliberately limit the maximum message size to 10 kilobytes. In practice, what is the statistical distribution of our message sizes? I'm sorry, I don't know. Yep.
How many messages a second do you deal with?
So, if I wasn't worried about copyright infringement, I would have gone to Meme Generator and gotten one of those sweet McDonald's X many billion served things, and it would have said 36 billion served today. Yeah, it's hundreds of thousands of messages a second. However, we find that with our current implementation, performance-wise, it can do 10,000 messages a second comfortably, and it can spike to 20, 30, maybe even 40,000 messages a second on a node before we get other weird side effects which we haven't managed to figure out.
What kind of things do you do to profile the Logplex to make sure you're getting that kind of
So I'm not quite sure if Jake Veruda, if you look back through other Erlang Factory conferences, has talked about a thing called Tempo. But it's a homegrown, I guess, low latency graphical dashboard. So we get graphs of message received, processed, drained, and dropped with 1 second resolution in near real time. And we do that in a pretty terribly straightforward and brain dead kind of way. Every second a process captures some counters from ets and publishes those to Redis PubSub. And when you hit an app we have called, I think, tempo-logplex, you get a little, it does like long polling or WebSockets or something, and gives you just a continuous chart of those things. So that's what we do for most of the profiling. I guess occasionally we'll go in with message tracing, like the Logplex system itself, all of these drain processes and input things tend to emit a bunch of logs themselves. And we drain quite a lot of that into a Splunk cluster and investigate logs after the fact that way. I guess I would also add that in the case of a VM exploding, doing post-mortem analysis with crash dump viewer or something similar has been exceedingly helpful for us. Particularly if your load balancers can cover for a failed node long enough for you to actually get a complete dump. Complete dumps are fantastic. You get a little web interface, you go to the process view, you sort by either message queue size or process heap size, and generally your problem leaps out at you. It's wonderful. Yep.
Have you had any notable performance gains or losses by changing the Erlang version when a new version comes out?
I'm not sure that we've had any particularly dramatic gains. My general sense is that it seems to improve. I guess way back when we had configured the system to run in non-SMP mode, and for a time that gave a performance benefit. But when we went through the input side and removed all of the accidental serialization, then turning SMP back on dramatically improved the throughput of the system. Yeah. Question from the back?
How does the speed of these logs how fast are these logs coming in compared to the hardware that we're porting?
I guess we have exceeded the capacity of our load balancers in front of this thing, which is just running stock HA proxy on reasonably beefy Amazon instances. Like, we now run, I think, 10 of those. We're doing more than a gigabit of logs as input. The cluster size for 36 billion messages a day is 40 nodes. I guess we're hoping to be able to drop that down or at least keep it stable relative to message volume growth. But yeah, that's the system as it stands today. Okay, thank you very much for your time. Oh, one more?
So you're using TCP syslog distribution, not UDP?
Yes.
Is there a reason for that? I mean, because UDP has better framing, right?
UDP does have better framing in that the frame is the packet. Yep. We had horrific problems with untracked loss with it. And partly that was kind of a system design thing, but the problem with running a UDP socket in active once mode is that it's very hard to get multi-process fan out on that, because as far as I can tell, only one process can be receiving off that socket at a time. I may be wrong on that. But even if that's right, if you add active once to that UDP socket, then every single message you do, you have to do an Erlang like port command, port control thing to change it back into active once mode again. And the cost of doing that quickly means that you start losing messages very rapidly. So we moved to TCP so that we could add some buffering on the sender side to at least cover, disconnection periods, that kind of thing. All right, thank you very much.